Hi everyone, my name is Adeyemi from the Department of Chemical Engineering at McMaster University, and I will be speaking on the dynamics and rheology of bidisperse polymer melts through a simplified molecular model. So regardless of the polymerization method employed, it's a given that there will be some degree of polydispersity, and that refers to the non-uniform distribution of chain lengths in a polymer sample. Sometimes different chain lengths are blended together to enhance their rheological properties or the mechanical strength of a sample. However, most of the established theories of polymer dynamics apply mainly to monodisperse samples. In this work, we focus on how the different chain lengths that make up a polydisperse sample affect each other's dynamics in a polymer melt. So we use molecular dynamic simulation for this work and represent our polymer chains with a bead spring model. And where the beads represent the monomers and the spring represents the bond between the monomers. So for the bonded monomers, we use affinity potential, which stands for finitely extensible nonlinear elastic, to describe the interaction between bonded particles. And for the non-bonded particles, we use the 12-6 Lennard-Jones potential, which describes the interaction at very short distances with a very repulsive force, and of course that's also weakly attractive at longer distances. For our idealized system, what we have done here is to systematically combine both long chains and short chains together. So for the short chains, the chain lengths that we considered ranged from 25 to 100, and then for the longest chain we considered we have a chain length of 350. So what we've done is to combine these two models together. For the first model, the short chains consist of a 70% by weight of the short chains, and then the long chains are present in a 30% mass fraction. Whereas for the second model, we have 30% by weight of the short chain and 70% by weight of the long chain. There are two main theoretical paradigms for describing the polymer melt dynamics, and this depends on the length of a polymer chain. The Rouse model describes the dynamics of the shorter chains, and here the relaxation after deformation stems primarily from the restoring entropic spring force against the viscous resistance of the solvent. Uh, the main conclusions are such that the diffusion coefficient scales inversely as the length, and there's a one-to-one proportionality of the viscosity as well as the chain length. When the chain, however, crosses a certain critical length, the Rouse model is inadequate, and the dynamics are better explained by the so-called tube model, where the evolution of the primitive chain is constrained along a contour in the so-called reptation motion. And here, the main conclusions are that the diffusion coefficient scales as the inverse of the chain length, and the viscosity scales to the 3.4 power of the chain. One way to study the dynamics of the individual chains is by tracking the time-dependent trajectory of a monomer and looking at how much it has moved over a given time like t. The square of this quantity, called the monomer mean square displacement, measures how fast the monomer is moving. This is commonly called G1. Similarly, we can also define the MSD of the center of mass of the whole chain as against the individual monomers this time around, and this is commonly referred to as G3. For unentangled chains, polymer theories predict that G1 of t will scale as t to the power of 1 at early times, and at intermediate times t to 1/2, and at later times in the diffusive regime it will scale as t to the power of 1. In the entangled regime, however, there's a significant slowing down when the topological constraints kick in, and the G1 of t scales as t to 1/4 in this particular regime. We see a similar scaling for G3 of t as well, where at early times t scales to the power of t1, and at intermediate times t to the 1/2, and at late times t to the power of 1. Before we delved into our bidisperse systems, we compare a monodisperse system with the theoretical predictions. The figure on the left shows the monomer MSD for the different chain lengths from n equals 25 to n equals 350. And we observe the different scaling regimes as predicted. And the center of mass MSD for the different chains is also shown on the right, which replicates the theoretical predictions that we have in theory. Buoyed by these results, we now delve into our bidisperse system. We see the results for the shortest chain we considered n equals 25 mix the different concentrations of the longest chain, which is n equals 350. The first panel shows the results on a log scale and would appear as though nothing much is going on. We plot the results, the same results on a linear scale, and we immediately see that the displacement for the monodisperse component, represented by the green line, has a much higher slope than the other concentrations at 30 and 70%. We further quantify this by measuring the self-diffusion coefficient, which is given by the slope of G3 at very long times. The The third panel shows that the division coefficient increases with increasing concentration of the n equals 25 chain. We similarly plotted the division coefficient of the longer chain n equals 350, and here we see that the converse is true. The division coefficient decreases with increasing concentration of n equals 350 chain, and this result is also true for all the bidisperse systems considered. That is where we have the 350 mixture, 350 mixtures, they're not shown in the slide. We therefore conclude that the displacement of the shorter chains is inhibited by the presence of the longer chains. Here we compare the dynamics of the longest chain, n equals 350, as a minority when mixed with different shorter chains as a solvent. That is, the shorter chains are in the majority. The graph of the left shows the log-log plot, and we also plot the same figure on a linear axis for emphasis. Here we observe that the shorter chains, the higher the displacement for the longer chains. The yellow line represents the mixture with 25, and the blue line is 50, and the red line is 100. We observe that the displacement is higher the shorter the added chain length. We further quantify this by calculating the division coefficient, which further confirms that the displacement is higher in the mixture with the shorter chains and slowest in a monodisperse sample by comparison. We similarly looked at the dynamics of the longest chain, n equals 350, as the majority chains mixed with the shorter chains, and we also observed similar results. The graph on the left, which is the log-log plot, is further amplified in a linear plot. Again, the yellow line represents the shortest chain at n equals 25. The green line is when it's mixed with n equals 50. The red line is when it's mixed with 100. And the blue line represents the pure 350. We also observed that the displacement is higher in the mixture with the shorter component, so that is n equals 25, and slowest in the monodisperse component. That is, the shorter chains, the greater the displacement of the longer chain. We however see that the displacement for the longer chains is higher when the shorter chains are in the majority, as shown in the previous slide. We now switch gears to solving the equation of motion for the beads. This is a rather formidable task because this requires solving a coupled differential equation. For a chain length of 25, that means solving 25 coupled differential equations, which can be rather cumbersome. However, by transforming the motion of the coupled beads to orthogonal coordinates, we're able to essentially decouple them, and we're able to further analyze this motion. The main takeaway here is that the relaxation of the subsegments of the chain, given as n over p, is independent and are indicated by the different modes of the chain. In this case, P equals 0 represents the center of mass of the chain, while P equals 1 represents the different subsegments. Of course, N over 2, P over 2 represents the half segment of the chain, and on like that it goes. The major conclusion here is that for a monodisperse sample, the relaxation of each subsegment is exponential. The figure on the left shows the exponential decay of n equals 25 at a mass fraction of 0.3 in a mixture with 350 as the majority component. The graph shows a very nice exponential decay. Although not shown on the slide here, when the shorter chain is the majority component, the shorter chain length also decays exponentially. As shown on the right panel, we recovered the relaxation time from the exponential decay at different mass fraction, and it also shows that as the concentration of the shorter chains increases, the relaxation time also decreases, further confirming the results we obtained from the mean square displacement analysis that the longer chains just hinder the dynamics of the shorter chains. But the simple exponential decay that applies to shorter chains no longer applies to chains that have significant topological interactions, as shown in the lower left panel, which is for the n equals 350 chain. Here, the significant topological interactions and excluded volume interactions are responsible for the departure from the exponential relaxation. The relaxation can, however, be described by a stretched exponential here, where the beta p in the exponential decay gives a measure of the departure from this exponential relaxation. By defining a different relaxation time as the integral of the stretched exponential, we can further compare the relaxation time for the longest chain. The top panels here, where n equals 350 with a mass fraction of 0.3, with a mixture of the different chain lengths 25, 50, and 100. And of course, the other panel where n equals 350 with a mass fraction of 0.7 for the 350. What we find here is that the relaxation time is longest for the pure species and shortest when combined with the shortest chain. The reason for the departure again is due to the stronger excluded volume effect. Now we turn to a more global picture that tells us about the bulk property of the mixture, and we have used the relaxation modulus for this purpose. Experimentally, the sample is placed in between two parallel plates and subjected to a step strain experiment. The relaxation modulus is then defined as the ratio of the stress remaining to the strain after a step strain deformation. Computationally, we calculate the relaxation modulus by taking the autocorrelation function of the off-diagonal components of the stress tensor. The right panel shows the relaxation modulus for our monodispersed samples, and by scaling the results by T1/2, we can readily see the departure of the results from Rouse dynamics. Here, the blue line represents the decay of the shortest chain length n equals 25, and the yellow line represents n equals 50. Both lines fall below the Rouse scaling and shows that these two chains are well in the Rouse regime. However, when n equals 100, which is given as the green line, the departure from the Rouse dynamics is becoming more apparent, and the red line that describes the relaxation modulus for n equals 350 shows a well-defined departure due to this entanglement effect. Here we show the relaxation modulus for the bidisperse systems as markers on the plots, and we have included the monodisperse components as lines for reference. Again, we scale our results by the Rouse scaling to amplify the entanglement effects and departure from Rouse scaling. In the left panel, what we see here is that the longer chains have a strong effect on the viscoelasticity of the mixture when it is the majority mass fraction. Compared to the shortest chains of the monodispersed components, that is n equals 25, 50, and 100, all the mixtures show a departure from the Rouse scaling indicated by the black line shown on the plot. In the second panel, however, where the shorter chains are in the majority, the shorter chains diluted the entanglement effects that's due to the longer chains. All the bidispersed systems sit right below the Rouse scaling line. We also see that the n equals 350 line, shown by the red line, is a lot much higher than this other systems. Now we finally conclude by evaluating a mixing rule for predicting the relaxation modulus of the mixture based on the individual relaxation profile of the constituent. Due to the different relaxation timescales in polydispersed samples, the relaxation modulus based on the pure repetition relaxation is inadequate in describing the relaxation modulus of the mixture. The contribution of the different components of a polydispersed mixture is accounted for through a mixing rule that relates the molecular weight distribution Wm of the mixture to the relaxation modulus. In the equation shown here, the Me is the entanglement molecular weight, while the Ftm is the Carnot function describing the relaxation profile for a monodispersed component. And we use the beta value of 2 here, which is based on the Doppler repetition model that assumes the repetition of a test chain also releases as constraints on the other chains. And then we compare the results for the 350-100 systems when 350 is the minority, as shown in the top panel below, and when 350 is also the majority, as shown in the bottom panel below. The yellow line represents the relaxation of the pure 350, and the blue line that of the pure 100. The red and green lines are the result of the simulation and the mixing rule, which shows that the mixing rule based on the double repetition predicts reasonably well the relaxation of the mixture. In conclusion, by using a simplified molecular model to represent our bidispersed systems, we have shown that the displacement of the shorter chains are inhibited by the longer chains, while the longer chains are sped up by the shorter chains. We have also shown that the shorter chains, the more the displacement for the longer chains. Also, we have shown that for both monodispersed components and bidispersed mixtures, the Rouse model still describes the relaxation of the shorter chains, while we see that the stretched exponential can be used in describing the relaxation of the longer chains. We also showed that the longer chains have a strong effect on the relaxation modulus of the mixture, especially when they're in the majority, by amplifying the entanglement effects. When the shorter chains are in the majority, they dilute the effects of the entanglement. We also showed that the double repetition model reasonably predicts the relaxation modulus of the mixtures. Thank you very much. And the resources provided by Sharpnet, Compute Canada, and Insert Acknowledged are well appreciated. We'll take the questions now.